Hello, everyone. So, welcome to the second supplementary lecture, which is actually going to be talking about the first problem in the assignment, where we are modeling a transmission line of a certain length L with a signal of a particular frequency lambda. But rather than using a full transmission line model, we are trying to divide this into a bunch of lumped elements n, where we are varying n all the way from 1 to infinity, with infinity being the continuum case. And we're trying to calculate what is the error in the output voltage. So the calculated output voltage for any given n minus the calculated output voltage when n is infinity, or the continuum case, over the input voltage. So we are calculating this error, and we want to plot this error as a function of n for different values of lambda to try to understand how the general rule of thumb that when L is greater than lambda over 10, we can assume a transmission line model. So now, how are you going to solve this question? So let's consider, so rather than considering the continuum case, let us assume that the transmission line is divided into n elements. So we have R, L, G, C. This will be the first element, and the second element, R, L, G, C. And imagine at the output, there's some load connected. So there's some load impedance ZL connected, right? So now what we're going to say is we have divided the transmission line into n elements. So this is element 1, this is element 2, and so on. And this would essentially be element n minus 1, and this would be element n. And so and each one of these resistor inductors is just going to be the resistance per unit length times the length over n, where L being the length of the transmission line. This is going to be LL over N. This is going to be GL over N and CL over N. So now what we are going to do is we are going to try to solve for the kth element. So if you consider the kth element, so how do the currents go? So the input voltage, this is Vn, this is I1, and this is going to be I2. And this voltage we're going to assume to be V1, and so on. So this voltage here is going to be Vn minus 1. And this current through this is going to be In minus 1. And so the final current that is flowing through the load is going to be In plus 1. And the voltage the voltage across the load is going to be Vn. So if you consider the kth element, of this lumped discrete transmission line model, so this is the kth element. So for this kth element, there is RL over N, LL over N, GL over N, CL over N. And so the current that is drawn by this is going to be IK, and the current at the output is going to be IK plus 1. The voltage at the input here is going to be Vk minus 1, and the voltage at the output here is going to be Vk. So now, for this kth element, if you use KVL and KCL, so if I use KVL, then Vk minus 1 minus of R plus J omega L times L over N times the current IK is going to be Vk. And similarly, if you use KCL, then IK minus V minus Vk over 1 over GL over N minus Vk divided by 1 over j omega c L over n is going to be ik plus 1. So this is from KVL and this is from KCL. And so if we rewrite these equations, so the first equation becomes Vk minus 1 over L over N is going to be minus R plus J omega L times Ik. And similarly, Ik plus 1 minus Ik over L over N is going to be essentially minus of G plus J omega C times Vk. So these equations, as you notice, are not called differential equations, but they're called as difference equations. And these difference equations are basically kind of a discrete version of a differential equation. So if we take the limit, that n tends to infinity, then the equation, so let's say this is equation 1, this is equation 2. If we take the limit n tends to infinity, these equations just become that dv of z with dz is equal to minus r plus j omega L I of z. And di of z dz is going to become minus g plus j omega c v of z. And so now you can combine these two equations and say that d square v of z with respect to dz square is equal to r plus j omega L times g plus j omega c, that's v of z. This can be treated as gamma square, and this essentially becomes just the wave equation. This is the wave equation, or the telegraph equation in the continuum case when n tends to infinity. And therefore, this is just going to be a discrete version of the same differential equation. When you have the length of the transmission line broken up into a bunch of n elements, but n not being infinite. So let's rewrite the difference equations and let's try to understand how to solve this problem. So we have the first difference equation, which is Vk minus 1 over L over N is equal to minus of R plus J omega L Ik. And Ik plus 1 minus Ik divided by L over N is going to be minus of G plus J omega C times Vk. But also you have a bunch of update equations that tells you how to go to k plus 1 from k or something like that. So Ik, so if you try Ik plus 1 is just going to be equal to Ik plus 1 minus Ik divided by L over N. This whole thing into L over N plus Ik. And Vk is going to be Vk minus 1 divided by L over N. This whole thing times L over N plus Vk minus 1. So these are basically the difference equations. It's telling you how the discretized slope or discretized variation in the voltage and current is along the length. While these are update equations that tells you how to go from one unit to the next, or how to go from, say, the kth element to the k plus 1 element, or the kth element to the k minus 1 element, right? So now let's again go back, let's rewrite our circuit. So our circuit is going to be R, L, G, U. This is going to be connected to some load impedance, which is going to set our boundary condition. So we know that this current, so the input is Vn. The input current, so this is the first element. This is the second element. This is going to be is basically the nth element, sorry, n minus 1th element. And this is going to be essentially the nth element. So the input here is going to be I sub 1, and this is going to be I sub 2, and this is going to be I sub 3, and so on. And here you're going to have, this is going to be IN minus 1, this is going to be IN, and this is going to be IN plus 1. And similarly for the voltages, this voltage here is going to be V1, this voltage is going to be V2, and therefore this voltage here is going to be Vn minus 1. Sorry. This voltage here is going to be Vn minus 1, and this voltage here is going to be Vn. So this is how we have defined, we have labeled our different voltages and currents. And if you have this for the kth element, these are the equations that tells you how to go. So now what we're going to do is, we know that the output load impedance is ZL. So now we are going to start with an algorithm, and how the algorithm is going to go is, we know we are going to assume some ZL and some output voltage Vn. So this is our starting condition. And then from the starting condition, we can now calculate what is In plus 1. So In plus 1 is just going to be Vn over ZL. And so now we have both In plus 1 and Vn. And now what we can do is, we can, using the In plus 1 and Vn, we can now calculate what is essentially, let me try to see. Yeah. So In plus 1 minus In over L over N is basically given by minus of G plus J omega C times Vn. So by substituting Vn here, we can calculate what is the slope. And then we know that In is going to be equal to In plus 1 minus of the slope, which is In plus 1 minus In over L over N times L over N. So now what we have done is, we have used this Vn in the difference equation to calculate the slope. And then we have used the slope again here. And we already know what In plus 1 is, which is based on the boundary condition, to now calculate In. And now that we have In, we can now calculate what is the slope in V. So Vn minus 1 over L over N is just going to be equal to minus R plus J omega L times In. So now this In is substituted here, and now we can get the slope, and then we can use it in the update equation for the voltage to get Vn minus 1 as Vn minus of this calculated slope, Vn minus 1 divided by L over N times L over N. So now what we have done by doing this is, we have started from ZL, Vn, which were the assumed quantities. And then from this, we calculated what is In plus 1. And then using the difference equations and the update equations, we have now calculated what is the value of In and Vn minus 1. So essentially, we have gone from Vn, In plus 1, and we have calculated what is Vn minus 1 and In. So we have gone one step back. So we have gone 1 unit back. And the same procedure of calculating the slope and then using it in the update equation and calculating the next stage can be continued to calculate now Vn minus 2, In minus 1, and so on. And this can be continued all the way till we go to the initial place, which is, we can calculate what is Vn, which is essentially just V0, and also what is I1. So by using this procedural method, we can go recursively and calculate assuming a certain boundary condition at the output, we can go all the way and calculate what is the input. And now the error is just going to be Vn minus V you would get if you assume n is infinity, or V naught. And this error can be calculated now for various values of lambda and for different values of n, and then can be plotted in the graph. So in order to do this completely analytically, it is quite difficult because it's obviously a recursive equation. So there are multiple steps to this. But one way is to solve this would be to assume some value of ZL and assume some value of Vn. So let's say Vn is 1 volt and ZL is 50 ohms. And then what we can do is also we can assume a certain characteristic, we can assume a certain value of RLGC, and then we can kind of back calculate this and get some number. And then we can calculate for different values of lambda and for different number of units n using something like MATLAB. We can compute and plot the error. And if you plot this error, epsilon, which is a function of essentially a function of both n and lambda, you'll find that there will be different plots. So the obviously if n is going to infinity, so as n tends to infinity, obviously you have the situation where the error is going to go to zero because it's just going to be V infinity minus V infinity. And then you would get a family of curves that look something like this. And what happens in this family of curves is that as your lambda increases, a lambda becomes as your lambda becomes much greater than L. So if your wavelength is much longer as compared to L, the graphs tends to go more like this. So this is as L is becoming smaller compared to lambda. And what this is telling you is that if L was large compared to lambda, then in this situation, when you go from the n equals infinity case and you reduce the number of sections, or you reduce the number of basically the number of ways you section the transmission line, the error grows very rapidly. But as L becomes smaller and smaller compared to lambda, what happens is it becomes more and more like the lumped element case. And so even if you use a smaller number of units, you'll find that the error is still comparatively lower, right? So your graph will basically have a trend like this. And if you make some assumptions as to the boundary condition in the source and the RLGC parameters and basically code this recursively in MATLAB and you plot it, you would get some behavior, some curve behavior like this. And what you will find is that if you assume that the length of the line is roughly, if the length of the line is roughly greater than lambda over 10, then if you don't go to a transmission line model, you will get around 5% error if you use a lump model. So you can basically get this result by going through this analysis. Thank you.